So first of all, I would like to thank you for coming here again, and I found the check here, round one. Right. Since we are talking about the cylindrical weights, I will use this one. And so first of all, I would like to say you, if you want to make me happy, please ask me whatever you want to ask. If I, unfortunately, I will be able to answer, I will answer. If fortunately I wouldn't be able to answer, we can discuss your query, of course. I will try to skip computations because we are definitely quite in late with respect to my program. But let me just make a few more remarks about the inequality we proved. That is in Rn, which is written as Rk times Rn minus k. And k is between 1 and n. Points are denoted if k is smaller than n as x, y. So for spherical weights, x is equal to xi. We proved that for any a, this is better to write in this way, k minus p plus a. So we were discussing about this.
A minus p.
A minus p. So for any u, let's. This is better. Okay, we proved it first by showing that this holds when capital N is equal to k, and then just integrating on the remaining variables. It seems that after integration in those variables, we get something in the left-hand side which is bigger. Actually, the constant here does not improve. I will indicate you three ways to prove that this is in any case the best constant. Moreover, if you remember the proof of this inequality, at this point we had some function, some power of some function, suitable power, such that this was equal to a constant, doesn't matter, the norm of x gamma minus p, doesn't matter. Okay. In the proof we used for some gamma we the gamma minus 2. Okay. So the trick was just to multiply it by u to the p. So in the left hand side we found we have made this computation. So at this point, this is some blah 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 x dot gradient of u, and in the first step this was an integration just in dx. Then we used Holder inequality blah 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 to conclude the proof. But this is the radial derivative of u with respect to the radial direction in the RK in this variable. So actually, at the first step, we used some older inequality that gives us some x to some power a gradient of u p 1 over p blah 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 blah, some other integral here. But that was really rough. And I mean, this is just you are evaluating here just the variation of u along radial directions in our K-space. That is a remark. But actually, if you put here the gradient in all the n variables of u, you don't improve the constant. Why? Okay, this can be checked in several ways. I will show you a few suggestions. But first, let me notice one very important thing, which is the role of dilations, since dilations appear also in the title of this mini course. So, first, well, assume that you have some other exponent b. Assume that you are hoping that this infimum is positive, given A, given P. Okay, then necessarily, if this is positive, necessarily B is exactly A minus P. You don't have any more chance, and this is because this ratio is invariant is invariant with respect to dilations in Rn. This is the C. Or that is because this integral and this integral rescale with the same ratio. I mean, if for any t positive, you test this and for u fixed in this space, you test this infimum with is equal to tx, then you make some computations. You make some computations and you estimate it by, of course it's better to fix a you use this ut to estimate from above CB, and you find here some t a minus p P minus A plus B, perhaps. Or something different, plus minus minus. So B has to be A minus P, otherwise you can let T go to infinity and prove that CB is 0. Okay. So this is a simple but important thing. Then the constant there is sharp. The constant there is sharp. Let me make, just to simplify notations, let me make remarks in the case k equals to n, but it's the same when for cylindrical, essentially the same. That constant is sharp, and because the function, say omega of x is equal to x to the power k minus p plus a, that enters several times, as you see, this function, which is not in the weighted LP space because because of the singularity, you know. This is not integrable, nor at 0, nor at the origin. So this function behaves very, very badly with the right-hand side, but also with the left-hand side. This function would like to achieve the best constant. Because it is a solution of the Euler-Lagrange equations in the punctured space. That constant and so on, very long. This is a solution of these equations in punctured space. Okay, so you can use omega to prove that that constant is sharp by just smoothing it with suitable cutoff functions, by truncating it at the origin and at infinity. Okay, so use some truncation cutoff, suitable cutoff function, and this one to test that one is the best constant possible. The second way to prove it, so 2, 1, 2, I don't know why this is the third proof. Well, the second one. I would like to remark that there is another proof which is less frequently used. Yes. Another proof would be the similar. I mean, to take some minus epsilon here for in the unit ball, plus epsilon, so you can regularize this omega also by multiplying it by suitable powers in the origin and at infinity. Okay, so okay, doesn't matter. So this is, I would like to point out your attention on another proof which is, as far as less commonly used, that uses some different non-compact group of transforms that acts nicely on radially symmetric functions. So fix U C infinity with compact support in Rk, which is equal to Rn, just to fix ideas, just to, and we take it radially symmetric and not trivial. Then for any t positive, we consider not this transform, but this transform. Let me call h some constant. What's h? H is this constant that enters many times. Okay, this is h. Then you make a number of computations, but those are really trivial. I will write it here. So in the cylindrical case, we just have to multiply this by something that depends only on y. Okay, doesn't matter. You make some computation. The result is this is the measure, since you can change coordinates, the measure of the unit sphere in Rk times t minus 1, the integral of s p minus 1 t u prime. U prime is a function of on the positive semi-axis. u is positive, I regard it as a function on a positive real axis. Minus h, so this is h minus 1 u force, and you don't have this over p. Well, some power that does not p perhaps to the p. I don't mitigate those computations, however. Now I check. So the same constant in front.
This S, what is this S?
This is the measure of when you change the coordinates. Yes. Sorry, this is an integral. You pass to polar coordinates and then change S. S is R to the power T. Computations S minus 1 phi to the power P yes. And so we find that the best possible constant, so let me call C A minus P, with the same definition, is smaller or equal than the ratio between this and this. This goes away, this goes away, so S P minus 1 T U prime minus H.
And phi is the same function as the above.
Here is phi and here is u. I always use those nice things to make me crazy. Now it is correct. U is a fixed radially symmetric function. I regard it as a function with compact support in the positive real line. Then I let t go to 0. What does it mean? It means that don't look at this. It means that I'm concentrating in some sense u on the boundary of the unit sphere, and so this disappears, and this is something like that up to h to the power p.
Why this one just T1 T prime disappears?
Because it is as t goes to 0. As t goes to 0, I said it. So this is less popular. No.
The powers of...
I mean, I am not very sure this is correct. It must be, I mean, it's written so. This is R minus 1 over T.
minus 1.
Yeah, minus 1. I have some.
Minus 1. Yeah.
I have some R here written. It is not correct. Fine. I mean, make your computations. It's this transform shows you. I mean, this is, as far as I know, less popular. Alexander, have you seen this? But I mean, it explains something.
I have seen this, but not in this context.
Okay. Well, just to understand the nature of inequalities. And well, in bounded domains, the third remark is that in bounded domains, due to the dilations, the role of dilations in Rn, if you assume that 0 is in omega, then the infimum of C infinity with compact support in omega minus the singular set of the same thing since you are minimizing on a smaller set, this is greater or equal than this constant HP. But because of the role of dilations, this is trivial. Because of the role of dilations, this is also smaller or equal than the constant on Rn. And so in bounded domains, the constant is the same. That's easy. This is because of dilations. Really simple, you take functions that almost realize the Hardy constant on Rn. You can assume that its support is its support is bounded by definition of this constant, since that constant is the sharp one, and then you can concentrate U in such a way you can use this transform this to show that you can assume that that function U has a support here, and if it has support here, this inequality is immediate. Now, for remark, this should be written before, never achieved. The constant H is never achieved in a very strong sense if P is greater than 1. I mean, there is no reasonable energy space in which you can find a function U, say with this finite and such that this ratio is the best constant. There are many ways to prove this. For instance, write down the Euler-Lagrange equations for a minimizer that does not exist, and essentially use this omega suitably cutted as test function. But for P is equal to 2, the proof is really evident because in the first lecture I have suggested, say for k equal n, for instance, this is just an example. This is the value of H in this case. This was greater or equal than the norm of gradient of x. Let's hope to some a minus a plus n to some power, to the right power. There is a power such that this holds for any test function u. And I mean, it's quite evident that this is always positive. I mean, this is just a justification why, at least in this case, you never reach the best constant. But I want to skip this. I want to ask you if you made the exercise about P equals 1. In contrast, the best Hardy constant for P equals 1 is always achieved by a plethora of extremals. Have you found the extremal? take any radial function. It is achieved on Rn and on any bounded domain. Actually, take any radial function like that is radially decreasing, and that positive, radially decreasing here, the positive, and then is 0 outside. Any such function achieves the Hardy constant. Try to believe. Try to believe. For p equals 1. Okay, it's just integration. You integrate by part ones.
That's for any domain which contains 0.
I mean, okay, yes. Otherwise, otherwise, if you have a bounded domain that does not contain 0, actually you are dealing with a Poincare inequality, and no. Because the distance function is bounded from above and from below. So it is achieved indeed. Okay. So say the Hardy constant is not achieved by concentration at infinity or by concentration vanishing. Concentration at infinity, speaking with using П.Л.Чебышева terminology, or by concentration at 0, or also by concentration on the unit sphere when p is greater than 1. All those things happen for p equals to 1, but for p equals to 1 you also find minimizers. And I found this simple remark in a paper by Grunau, Mitidieri, and somebody else. Well, the last remark, I will not make computation. The last remark, I don't know which number is that if if the weight b is integrable, so it means a minus p is greater than minus k. Okay, this is the problem. So if a, that is bigger than p minus k, then the Hardy inequality holds with the same base constant for any u in C infinity with compact support in Rn. This is also for cylindrical stuffs. Just take a function here. Take a function here and cut it suitably at the origin. You can do it and sending this goes to 0 nicely when a is greater than p minus 2. So this is phi h is equal to 0 in the disk of radius 1 over h, is 1 the disk in the outside the disk, the ball of radius say 2 over h. This is phi h. You first use apply the Hardy inequality with this function that vanishes on this is just a function on x. Vanishes on the singular set, and that you can pass to the limit as h tends to infinity when a is greater than p minus k. Okay, believe me, I will skip this part because I want to finally reach the main part. I will call the M, not of course because of Musina, but because of much more outstanding mathematician. So I will, from now on, this will be was supposed to be the main. So this is an integration in C, cylindrical weights. I will not consider singular weights, so I will limit myself in asking a greater than P minus n. So I will look for inequalities of this form.
P minus n or P minus k?
Exactly, that's the core. This is the reason why I decided to talk about cylindrical weights. So let us forget about this. Let us forget about this. I mean, oh, perhaps I should also erase something here to be able to write. So, for the moment, the problem is study equations, study inequalities like that, where you have a weight that is the weights that are power of the distance from some subspace of codimension k. Okay, I'm much more well organized now, and also that one I will erase it after. So say I want those things to be I want to be able to write first of all those two inequalities for any u with compact support. Not only u equals to 0 on the singular set. So I need to ask that a is greater to minus k, and minus b greater than minus k. I can write the two integrals for any u. Then I want I'm interested to know in the case q equals to p, but in the case q greater than p, and because q equals to p is the hard inequality, q smaller to p is that less hopeful, because this is an unbounded domain. So q greater than p. And then, of course, and if I hope that this constant given p given q is positive, I also have to ask that q is smaller or equal than the critical Sobolev exponent if n is greater than p.
What is n? N capital, yeah?
Yes. Is it clear to you why this is essential to hope that to have a positive constant here? Because that is totally independent of the presence of the weights here. When q is greater, you can concentrate, you take function u and concentrate them in points where this is not 0. So actually, if this inequality does not hold for any u with a positive constant, you cannot hope in some sense for supercritical q to have that this holds. I think you are quite familiar with the Sobolev inequality. In any case, we will need this also in the proof. Then another necessary condition comes out from investigating how dilations act on the left-hand side and on the right-hand side. It's some easy argument, as I made before. When Q was equal to P, this minus P, pay attention, has to be A minus P. And in this case, because of the role of dilations, B must be N minus Q, N minus P plus A over P. I apologize for the fact that this is not the standard notation that has been used, for instance, by Caffarelli con Nirenberg. That is a very, very cited paper. But actually, I started to study those kinds of inequalities in the spherical case in 1998, when I didn't know this Caffarelli con Nirenberg paper, so I was using my own notation, and at that time I was already so old that I never changed my notation. So if you look at the famous paper by Caffarelli con Nirenberg that appeared in Compositio in 1984, you will find the different notations. Of course, in this paper they studied the case k equals n, and you can, if you go to MatchNet, for instance, you can see that I have to say those. Finally, I'm old enough to say that my paper with Paolo Caldiroli was the 8th paper in 1999 or something like that. The 8th paper citing Caffarelli con Nirenberg paper, the 8th one. So and then now it has hundreds of citations. This paper, not this, surely. The question is, why M? Not because of Musina, of course, but because of Mazia. That actually proved this inequality in the right assumptions in at least, before. So it's a book is in 85, but the German version was I guess he proved in 80. And there is also a paper you suggest, but it's written in Russia, so I cannot.
This inequality in different terms was proved by Valentin Petrovich Ilyin from Leningrad in 1961.
And I was not old in that time, no, definitely. But people knows this inequality in the spherical case, actually in a little bit larger setting, as the Caffarelli con Nirenberg inequalities. I will call them Mazia inequalities because those are cylindrical. Well, in the Mazia's book, actually, one can find a proof for, I don't remember, k greater or equal than 2. And you have to look for the proof around the book. So, I should say it's not totally easy to find the proof. Now, what is the theorem? The theorem is that if k is between 1 and, of course, the Mazir result is much more, okay, it seems it has this restriction, but it is much more general than this. So the theorem is that, now you can see that you can immediately be more careful with this integrability assumptions, because B must be this one. So so you can rewrite more explicitly those two things. So let me erase the integrability assumptions. P is greater or equal than 1, but I will not deal with the existence of extremals for P equals 1 by things I like reflexive spaces. And the theorem is that I think I will prove it in the second part. Okay, this is an assumption, this is an assumption, this is an assumption, and as concern summability is A greater than P minus N to have this positive. And in particular, if A is greater than P minus N, okay, that is weaker than P minus K. So we are not asking, by the way, in general, that the hard inequality holds. And Q, but in this case, you also need that Q is greater than N minus K over N minus P plus A. Those two extra assumptions are not extra assumptions, are needed in order to have that weights are locally integrable. Then MO holds with a positive constant. So let me just draw, to finish this first lecture, let me just draw the difference between the Caffarelli-Nirenberg spherical weights and the cylindrical weights. Well, in the spherical weights, the assumptions are A greater than P minus N. Of course, this is not really nice. Okay, let me, if K is smaller than N, otherwise this means 0, say. Okay. So I was just trying to draw, you have a nice draw here. This is a draw, let me assume that N is greater than P. So this is A, and these are the admissible Q I can get, P x fist. Okay. So A must start from P minus N. This is P, this is P star, the critical Sobolev exponent. Okay, and I can take Q in this rectangle. This is excluded. The critical Sobolev exponent is included. This is also the range of exponents for which the hard inequality holds. That's for the spherical case. In the cylindrical case, I have P minus n here, but I have P minus k here. And I have this curve, decreasing curve, that is the curve given by this, say, Q hat. I must I must choose Q be above this hyperbola, this curve, and not larger than P star. Okay, and strictly larger than P because I am interested in this case. No, okay, I can take also P. I can. And the Mazia inequality holds in all this strip, but also here. And the hard inequality with cylindrical weights, that one we wrote somewhere here, holds for U in C infinity with compact support in Rn only when these weights were integrable. So it holds here. Okay, while the Mazia inequality, sorry, I cannot take here. Q must be above the hyperbola. While the Mazia inequality holds also here and here. So you win a region of exponents, that one, in which the hard inequality fails with cylindrical weights, while Mazia inequality holds. That makes really a difference. And there are many problems, open problems, that are focused in this case. So before the proof, I should say remarks. I already draw a remark and already erase it. I don't know if this was a good idea. So two applications of this inequality for truly cylindrical weights when n is equal to 3. So the first one is k equals 2. So the singular set is a line because n is equal to 3. So we are why this has some importance, because so this is say a vector in R2. This was our notation before. This has some importance for some problem in astrophysics, and that was the object of that paper by Badiale Tarantello I mentioned last time. Badiale Tarantello from Torino and Roma Tor Vergata. It has some connection in astrophysics. I'm not will be involved in that. Now, if we apply that, which are and P equals 2, so the invariant case, so we have inequality like, and also let me say A equals 0 just to simplify, and also not P 2. So So since n is 3 is greater than 2, q must be taken smaller than the Sobolev exponent to n over n minus 2, which is 6. This is capital N. Since n is equal to 3. And this inequality holds with a positive constant. P is given by that formula. Provided that Q is greater than 2, but also that Q is greater than 2. 3 minus 2 is 1. 3 minus 2 is 1. N minus 2. Which is 2. So this is because we want to skip the hard inequality. We want Q greater than P. This is the additional assumption in the theorem, okay? But they are the same assumption. For Q equals to P equals to 2, the hard inequality does not hold. Nevertheless, this Sobolev inequality, Sobolev type inequality holds for any Q greater than 2 and smaller or equal than 2n over n minus 2. What is B? B is equal to 3 minus Q 1 plus Q over 2. Okay, of course, when Q is the critical Sobolev exponent, then B is 0. Okay, and so when Q is the critical exponent, this disappears, and this is exactly the true Sobolev inequality. But when Q is strictly smaller than the Sobolev inequality, then this holds in R3. I mean, when Q is smaller than the critical, is different from the critical Sobolev inequality, you cannot prove this without a weight. And this was so a Sobolev type, weighted Sobolev type inequality holds even if the hard inequality does not hold. Second example, that a connection with somehow important problem with applications was pointed out by Mancini, Gianni Mancini. Mancini from Rome 3 and his collaborators, Sandeep and other people. Sandeep is from Bangalore and other people. I have to write Gianni Mancini because he had got a student whose name was Gabriele Mancini. So G. Mancini, they were not relatives at all. But they have, it was a, and Gabriele Mancini is now a student in SISA. So the case is n equals 3, k equals 1. So the singular set is a plane. It means that in this case, the singular set disconnects the domain. So, for instance, we can restrict our attention to C infinity with compact support functions in R plus times R2, because now Rk is R. But that disconnects, the singular set disconnects the domain. So now x is a positive real number and y now is a vector in R2. Okay, in this case, actually the hard inequality holds with cylindrical weights and A equals 0 and P equals 2 again. In this case, for functions here, the hard inequality holds. The hard inequality we proved. And that hard inequality tells you okay, this is not. The hard inequality holds, but we also have inequality like that. Let me call this space the positive half physical space, R3 plus. Okay, half space. So this inequality holds. With B given by the usual rule. Provided that what are you written here? What I wrote here. For any Q, no. This is not the right application I would give. No, but Q between 2 and 6 seems to be totally trivial. This is not the remark by Gianni Mancini. No, I have to write better the remark by Gianni Mancini, which is as follows. Well, the hard inequality tells you that this is quantity is positive for functions here. And by a trick I mentioned in the first lecture, it turns out that this is greater or equal than the integral x. Well, let me take also q is equal to 2n over n minus 2. So the critical Sobolev exponent. So how to connect this and this? You use this, the usual trick that tells you that for functions with support in the half space, you have this trick that this is the Hardy constant. Okay? You have this trick, I forget, no, I should have made a remark before, but I don't find it here. Let me say, let me write down a more general inequality that has been noticed by Mazia for k greater or equal than 2 or than 3, I don't know, something, and also extended by Gianni Mancini and Sandeep in this case, k equals to 1. So a corollary of that inequality tells exactly in the case p equals 2 that gradient of u squared minus k minus 2 over 2 squared, this is more generally.
U squared.
You can put also sublinear, the smaller exponents here, doesn't matter. This holds for any u actually is infinity with compact support in Rn minus the set x equals 0 perhaps, so then you can so this holds.
What is Q in the right-hand side? C.
This holds if k is strictly smaller than n. You can see that this coincides with this when k is equal to 1. Of course, why? Because in this case, the extra assumption here is satisfied. How to prove this? You substitute. Let me see if it is written here somewhere. Okay, you pass from u of x to x 2 minus k over 2 v of x. Okay, and you notice this left-hand side here. This is a trick I already mentioned. If k is strictly smaller than n, then you are allowed to take a is equal to p minus k. 2 minus k. And you can apply this theorem for any q that is strictly greater than p, that is than 2. And of course, q smaller or equal than 2 star if n is greater or equal than 3. You made side computations to say that this left-hand side is equal to this integral up to this functional change. Then you apply the Musina inequality. You find that for those q, you have a positive constant such that up to some exponent given by that is positive. This is the Musina inequality, and then you go back to u and say that, so for instance, 2n over, no, I don't know, yes, 2n over n minus 2, so n minus 2 over n. You go back to u and you find that this is u to the critical Sobolev exponent 2 over 2 star. Okay, so I mean up to this transform, okay, you get this inequality like that for any function u that vanish on the singular set. For instance, you get this inequality for n equals 3 and k equals 1. I have to mention two important facts. The first is that, let me call, an inequality like Musina star fails for k equals n. That has been proved by Bresis Vasquez. Don't know how to write the Vasquez.
Who is? Q. Was Q.
Some u is missing, of course. And can be also deduced by as a corollary of some recent non-existence results by Bresis Dupagny-Tezay. While in the cylindrical case, you can improve the hard inequality by putting some norm for and this for functions defined on all space. Okay. The second remark I want to make in this context is that this really nice trick, that is this quantity here is equal to this quantity, holds sharply for p equals 2. P here. As far as I know, but I should check, you should check the more recent literature, for P different from 2, it is not clear how to write something like that, but you should check in the literature. Okay. This leads you to different inequalities, because this, thanks to this inequality, you can define a space which is larger than the usual D12 space. Larger. Okay, and there are many open problems, as far as I know, concerning the existence of extremals for that. That includes the Gianni Mancini, Sandeep, and Citra inequality I wrote here. And what they observed is that this inequality is related to the Sobolev inequality. Actually, it is equivalent to the Sobolev inequality in the hyperbolic ball, if somebody is interested. Sobolev and the three-dimensional hyperbolic ball. Actually, the hard inequality in this context is equivalent to the Poincare inequality in the hyperbolic ball, and this Bezier inequality is equivalent to the Sobolev inequality in the hyperbolic ball. And there are many problems, so you can find out concerning hyperbolic balls. I don't want to enter into details. I just want to say that the hyperbolic ball is a true three-dimensional ball with a metric that became singular on the boundary of the ball, and but also there is a representation of the hyperbolic ball through the half space. And this has been pointed out also in that paper. Okay, let us sketch the proof. Okay, the proof of the theorem up there. The conclusion can be proved. The inequality up there can be proved very easily in the following cases. When both the Hardy and the Sobolev inequality holds true, this is the hard inequality. So this holds for U C infinity with compact support in Rn whenever A is greater than P minus K. That is worse than P minus N. And the Sobolev inequality tells you, this is Hardy, this is Sobolev, that for functions there, this holds if n is greater than p and take p star np over n minus p. So when the hard inequality and the Sobolev inequality are available, then by interpolating them via Helder inequality, you are able to cover a number of cases in these conclusions. For sure, all the cases when A is equal to 0. But then you can also capture the case when A is non-zero by some simple trick. But that inequality holds also when Sobolev does not hold, and in the cylindrical case, it holds also when Hardy does not hold. So It has been, well, I was not able, at the time I was studying those inequalities, I was not able, actually, I apologize, I was not able to read the proof in Mazia book. And Caffarelli con Nierenberg used pointwise inequality that does not behave so nicely for cylindrical weights. But in any case, the proof is not very difficult. There are several steps in the proof. The first step is the Sobolev inequality for P equals 1. A equals 0, Sobolev inequality. No. The first step, you don't have a Sobolev inequality for P equals 1 if n is equal to 1. So the first step is n equal 1. The first step is n equal 1. I use a trick. In this case, you don't have cylindrical weights. You only have spherical weights. Ciao. How are you? Okay. Well, I use the Emden-Flower transform. U, first let me take U. Actually, in infinity with compact support in the positive half line. All the arguments I will present here. First, we will prove first for functions that vanish on the singular set. But then you can capture all those functions via density argument. I will never say it again anymore. So I have to prove that under some assumptions that inequality holds. And so since I'm working in the half line, I can simply write this way. X is a positive number, u prime of x to the p. I just have to write this one and to put something below. Well, I put h. Those famous h is n minus p plus a over p. Now, the h I used before with n equals 1, and I use the Emden-Flower transform. That is, I put this function u into a function on the real line, so that g is a infinity with compact support function in R. Through this Emden-Flower transform, I make some easy computation, and it turns out that this is minus, I don't remember here, before I wrote minus, here I write plus. It doesn't matter, actually, it doesn't matter if it is plus or minus. Perhaps it's plus, I don't know. In any case, I have the absolute value here. While if B is the right one, who should be B here? N is equal to 1 minus 1 plus Q, and that is the constant H. That constant. U to the Q is simply equal, these are integrals on 0 plus infinity, these are integral on the whole real line, to G to the power Q. So in the first, in this one-dimensional case, we wonder if the constant is positive or not. Is okay. If P is equal to 2, if P is equal to 2, then you can compute this explicitly, integrate by parts. The integral by the double product is 0. You have some GG prime is 0. And this Emden forward transform, 2 over Q. Pardon? And this Emden forward transform has been largely used for the Hilbertian Kp is equal to 2, exactly because of this. Because H is not 0, because among the assumptions we have that A is greater than 1 minus P, so H is not 0, and this is obviously an equivalent norm on W1P. Okay? And for the same reason, for P different from 2, this computation is, of course, is not possible, and people didn't use it, but I'd use it. Since he is sleeping, I can say. This is not R, N is R. I have used it. And I proved that this is positive also in a more general case. Why? Because this in the numerator is an equivalent norm. It is equivalent in any case also when P is not 2, is equivalent to the standard norm in W1P of R. Why? Because the hard inequality that holds in our situation that is x to the power a u prime to the power p. Now it holds. Let me think. P minus 1, something like y, h, sorry. H indeed is positive. This is the hard inequality be proved in several ways. You write it as a G. And the hard inequality simply is this inequality in terms of G. Okay? And trivially, this is smaller or equal than any reasonable standard norm you want to put on W1P. So this is smaller, is controlled by the standard norm in W1P. To check that this is an equivalent norm, you have to check that this is greater or equal than some constant. The standard norm, say g prime of p plus the integral of g of p. And then you are done. This is an equivalent norm. It is not difficult to prove that this controls the standard norm in W1P. Why? Because you have the hard inequality that reads like this for G. And to prove this, you only have to check that if you have a sequence that goes to 0 in this norm, then necessarily it goes to 0 in this norm. But if you have a sequence GH such that this norm goes to 0, that is G prime of H plus H, G of H goes to 0 in LP, then you can use this hard inequality to have that GH goes to 0 in H in LP. But if GH goes to 0 in LP, and this is your assumptions, then clearly also G prime of H goes to 0 in LP. That means that G goes to 0 in the W1P norm. So actually, this is also when P is equal, if P is equal to 2, then this is evidently explicitly an equivalent norm, but in any case, for any P, it is an equivalent norm. And so this is positive simply because you know that the space W1P of R is it true? Is embedded in LQ of R for any Q smaller than infinity or greater or equal than P. Is it true? Yes. That's end the story for n equal 1. And I used this equivalent norm on R also in a more general setting recently. Well, let us go on with the case n greater or equal than 2, because the one-dimensional case is over. And then this is the second step. You take P equals 1. And so you have a critical exponent that is 1 star is NP over n minus P for P equals 1. So the second step is this one with A equals 0. That is in this setting and Q equals the Sobolev exponent. The second step is nothing but, let me write for V, the Sobolev inequality. I will not prove it. I assume that you already proved. Actually, this is the Gagliardo Nirenberg Sobolev inequality, exactly because P is equal to 1. Because the proof via hard deletable Sobolev inequality fails for P equals 1. But it's proved by induction. I mean, you can find it in textbooks. I will skip it. Now, why I wrote this with V? Because the third step is to put some coefficient here. So still P is equal to 1. And K is between 1 and n. Sorry. But a greater than 1 minus k, that is worst, and still q critical. Well, because of this, the hard inequality holds, and you simply apply the Sobolev inequality gradient of u. U is always a function with compact support that vanish on the singular set by safely. Then one can argue by no, let me start in a different with a different direction from the LQ norm. So we want to prove that, let me compute B. B in this case is equal to n minus Q is n over n minus 1, n minus 1 plus a over n, over p, which is 1 in this case. So this cancel with this. And so B is nothing but NA minus NA over N minus 1.
Excuse me, in the previous case, why in the previous case B was equal to 0?
Sorry, I haven't computed. Oh, well, you can look at it.
The previous one, so let's say that B equals...
I mean, always a remark. Take N greater than P. Take Q is equal to P star, and then B is equal to N minus for any A. So this is N P over N minus P, N minus P plus A over P. P and P cancels, but here, this times here is n. So B, whatever n is, whatever A is this one in the critical case. In particular, B is 0 if A is 0. Sorry. And now we have NA over N minus 1. So we have minus B there, so we have NA over N minus 1, which is minus B for U in the critical case, 1 star, N over N minus 1. We write it as norm of X. Let me write N over N minus 1, which is 1 star. You can see here I have N over N minus 1. Simply a trick. Then I apply the previous step to with V equals to this function. So this is the function V, and this is going to be smaller or equal than the integral of the gradient x to the a u to the power n over n minus 1, of course with some power n minus 1 over n, otherwise it is false, of course. Then you compute this, you make some elementary inequalities. So this is inside the moduli is a sum of the two derivatives, I mean the usual rule, but up to a constant you can write it as the sorry, x to the a. No. You do not have any more here. Sorry. So this is simple the triangle inequality. Sorry, we have I've applied the Sobolev inequality with p equals 1, so this is 1. Otherwise, plus the integral of say u exactly you have a x to the power a minus 1. That comes from the gradient of the norm of x to the a. Okay? This is exactly what appears in the hard inequality. So put some absolute value here. This is the right-hand side in the hard inequality up there with p equals 1. So this is controlled by something like this. Of course, this holds up to constants. So you have perhaps another constant here, x to the a gradient of u. So actually this completes the picture for p equals 1. So the theorem, Mazia theorem, is completely proved when p is equal to 1. And now actually for p greater than 1, we'll just use a standard trick that is try to apply what you know, the inequalities you know, not for u, but for some power of u. Now you have to use this spatial tool. You know, this I don't like this one because I remember when I wash the windows of my house. In these days I would like to forget. Let me try if it's possible to go. I would, if you agree, I would just show the right. I mean.
Approximately now, it should be break between two lectures.
Now indeed I just otherwise I have to prove all things the next one. So I prefer to I prefer. So you have to estimate from above something like that, and you want to prove. You want to apply this inequality of step 3. Not to u, but to some power of u. That's all. So you want to apply this to some power. Of course, you have to no, not exactly. I mean, no, there is one step beyond, before. There is one step more. I will do it. I mean, just it's because of Sasha. Should I finish this proof, or should I? Well, tell me. No,
It's for
like,
you.
it's for me. So I prefer to stop it here. I mean, so I will just so the first step is first step. I mean, it's not totally proved. This is proved. I skipped this. Mazia inequality is proved for P equals 1 and Q equals to the critical Sobolev exponent. But then the fourth step is always P equals 1, A as before, say, and Q greater than 1 and between and below the Sobolev exponent. So you only need to interpolate so you write this as Tn over n minus 1 plus 1 minus t, which is a convex combination between this exponent and this exponent. Okay? And so you simply write, everything goes well. You just interpolate n minus 1. Here you have n over n minus 1 perhaps to the power t. And then it remains perhaps some x to the power a minus 1 moduli of u to 1 minus t. You interpolate and you get all the q's between Hardy and Sobolev case. Everything is fine. I mean, it turns out that B is this plus this. It's a miracle, but it is. The last step is what I said before. The last step is the final one up to the density. I will skip totally the density. I just write down this. The next is the general case. In the general case, you take tau is equal to q over p prime minus 1. Evidently, it's greater than 1. Fantastic. I wrote that the tau is between 0 and 1. Fantastic. Sigma q over this tau. And alpha is equal to tau. The Hardy constant. What comes in the Hardy inequality. By the way, notice that B was equal to n minus qh. T minus h plus 1 minus n. Then you define u sub tau, some power of u. And you apply the equality 4 with the equality 4 with sorry, a moment, don't, I wish to finish. Some gamma, the b tilde, some b tilde, u tau, this tau, to the power sigma, where sigma turns out to be between n over n minus 1 and 1. Okay? If you want, I can do it again in detail in the next lecture. But I mean, this is a very standard trick. You prove something essentially for p equals 1, and then you use your result for p equals 1 with some power of u instead of u to get the result for gradient of u to the power p. That's really standard. It only needs to find alpha. Don't know what is. Perhaps alpha is somewhere here in this b tilde. B tilde is the right one. You apply step 4. So this up to some constant e is x to some power alpha. Here is alpha. Gradient u tau to the power p equals 1, and then of course to the sigma. To the sigma perhaps. And you compute this gradient. Should I, if you want, I can go on or I can stop. Referendum. Let's vote.
Just a question. In the previous step, step 4.
Yeah.
So once you have written those two,
you don't believe
the two products. So now then, let's say for the first one you apply the previous inequality. For the second one,
it's Hardy.
Second one Hardy.
Yeah. You interpolate between Sobolev and Hardy. I mean, if you have an equality, it's standard. Also, when you prove that for bounded domains, H12 is embedded in LQ for any Q between 2 and 2 star. What you do is to prove the Poincaré inequality in bounded domains. To prove the Poincaré inequalities, to prove the Sobolev inequalities, then you obtain by interpolation all the inequalities in between them. And also on Rn, I mean, you have Rn intersection with some L tau spaces.
Essentially, you interpolate between Sobolev and Hardy here. Yeah.
I mean, I noticed at the beginning that cylindrical inequalities, inequality with cylindrical weights may hold when, first case, you have Hardy and Sobolev, in that case interpolation. But it also holds when you have Hardy and not Sobolev, trouble. It also may hold when nor Hardy, neither Sobolev inequality holds. What is the trick? The trick is, first step, prove the theorem for the case p equals 1. Why? Because when p is equal to 1, everything holds. P is so small then that you have Sobolev and you have Hardy. Then use this standard trick of, so and interpolate between Hardy and Sobolev. Then use the standard trick that is apply what we have proved for p equals to 1, not to u, but to some power of, that's really an Italian accent, isn't it? not to you, but some power of tau. Tau, sorry, tau, that's tau, not tutti. Tau, that's tau. Tau. Okay, because I wrote here t and here tau, as usual. And then, believe me, you just have to make the nice choice of all those parameters, and finally everything, thanks to the assumptions you made, everything goes well, and you get all the proof. That is not really, you will never find it in Mazia book, never. Starting from the fact that small g, let small g be, what is small g in Mazia book? Bounded upper domain. And that's hard to me, really hard, to recall that g, small g is a bounded domain.